chapter 5 here. Starting into chapter 5, our title today says extreme values of a function. You have been introduced to extreme values of a function with math vocabulary. They are called extrema. I don't know if necessarily this first table needs to be written down, but it is a reminder that you know what these are. I know for sure back in pre-calc you guys talked about extrema. And another word for extrema are maximums and minimums. Now, there are two different types of extrema. There are absolute extrema, and then there are relative or local extrema. And I think a lot of times in our pre-calc class we'll refer to them as like a relative max or a relative min. Our calculus book calls them local. It's the same thing, and it doesn't matter to me which word you use. Basically, it's indicating that you know that it is a maximum value or a minimum value relative to the things around it, but it is not the overall highest value in that picture. This is a picture I took out of your book, and it kind of just goes through the things that I want to point out. So like this right here, anytime it's the top of a hill, we would call that a maximum. So we've got the top of a hill here. Here we've got a maximum. And the difference between those two maximums, this is a top of a hill, but not the highest point in our graph, so it's called local or relative, where this one is the highest point in that entire graph, which we would call absolute. They do identify three minimums, including the endpoints of that function. And that is one thing that may be new to you, is including an endpoint as a maximum or a minimum will happen now. And so again, this one would be our absolute minimum, a local or relative minimum, and a local or relative minimum there. One of the things you want to make sure you do is, as you are describing your extrema, is that you kind of format it in the correct way. And so we will identify what it is. So our maximum or minimum. So this would be our absolute or local relative, max or min. Okay. And then we would say of, and then we will say what value. So this would be the y value at x equals whatever x value that is located at. So it's kind of like a three-step process to this. What type of extrema are we looking at? What is it? Where is it? Okay. We'll kind of format it always in that sense there. So we're going to use a very common function that we know a lot about to kind of go through finding some absolute. Now this one just asks us for the absolute, so if it's not an absolute, we would not include it. But finding any absolute extrema of the following function over the given interval. And again, this is one that we know pretty well. Y equals x squared. The first interval they ask us to look at would be from negative infinity to infinity. So that function, okay? So if we were to look at that x squared graph, I know what that looks like. That's 0, 0, 1 squared is 1, 2 squared is 4, negative 1, 1, negative 2, 4. And we're looking at that parabola right there. So we're looking for any tops of hills, any bottoms of valleys, any place where our graph would end at a high or low point. Do we have any absolute extrema in this picture? Yeah. We have an absolute minimum, right? We have a lowest point here. So practicing how we identify that, that would be an absolute min of, and then we look at that ordered pair where that point is located. That point is at 0, 0, right? So it's got a y value of 0 and an x value of 0, which is both. So it would be an absolute minimum of the y value of 0 at x equals 0. Question so far? Okay, so what if I restrict what part of that picture we're looking at? What does that impact about my answer? What if we only look at that function from 0 to 2? So I can erase, you might draw a new picture for yourself. If I only look at that from 0 to 2, that means we would start here at 0 and go up to 2. Okay. So what does that change about my absolute extrema? it adds another one, doesn't it? So now not only do I still have the minimum that's sitting there at 0, 0, right, is we also now have a maximum point in this picture. So this one is not going to change, absolute min. But we added an absolute max of, and again, let's look at that point. That point is at 2, 4. So a y value of 4 at an x value of 2. Maximum value of 4 at x equals 2. Good so far? Okay. What is different about what I just had up there compared to what I'm asking you now? It's an open circle. The parentheses means we don't include 0. So I can come over here and instead of that, it would be like that, right? What does that change about my extrema? Yeah. The minimum that we listed above, the absolute min of 0 at x equals 0, is not included in this interval, is it? So that's not a minimum in this picture. And the hard part about this is understanding what is the minimum of this picture. Well, if we are approaching an open dot, there is no minimum there, because I will continue forever to get closer and closer and closer to that, but never actually get to 0. So there is no actual minimum value in this picture right here with the open dot. There is still a maximum. Same point, I'll have a maximum at 4 at x equals 2. Okay. And then our last one, if I change that interval from 0 to 2, but it's an open interval, again, that would change this dot to an open circle. So now what are my absolute extrema? None, right? I don't have any absolute extrema, which is okay. And basically what I'm using this example to show you, because we kind of looked at the same thing over and over and over again, and it's one we're pretty familiar with, but looking at the difference that of the impact of the interval and whether the interval was open or closed and what that meant about our extrema, that leads us into this thing that is called the extreme value theorem. Now, the function I handed you was x squared. That is a continuous function. And the extreme value theorem has two parts to its condition, and it says that it is a continuous function, and we are looking at it on a closed interval. And if you think about the examples we just did on the last page, one of those had a closed interval. If those two things are true, it's a continuous function, and it is a closed interval, I can guarantee by the extreme value theorem that we will have both types of extrema, a maximum and a minimum. But if one of those fails, it's not a continuous function, it is not on a closed interval, then everything is fair game. It doesn't mean that we won't have extrema. All it means is that we are not guaranteed extrema. Okay? And all that does is kind of help you know whether or not you've found everything as we move forward into finding maxes and mins. The reason the closed interval is so important is that is a potential location of our maxes and mins. And if there isn't any others, that's where they will be located. Okay? And this next part is so huge. Just look at this part for just a second. And that is critical points. Okay? You are going to hear that word like every other problem for a long time. And that is this. A critical point is a point on the interior of our domain at which either our derivative equals 0 or our derivative does not exist or is undefined. Critical points are one of the places that your function can have a max or a min. So what we're going to do on each problem when they ask us to find these extrema is to make up a list of the critical points, but then also the endpoints of our interval. So I'm going to reword that last thing. It says extreme values occur at critical points or endpoints of a closed interval to something like less mathy. extreme values, when they ask us, when the question is to find maxes or mins of our function, they will be located at one of these places, either at the ends of the interval, like A and B. They will happen when I take my derivative and set it equal to 0. They will happen when my derivative is undefined. And undefined for our derivative typically happens when we're looking at a fraction, and that was when the bottom of the fraction is 0, right? So undefined at that. And so that's the list. We will check off all of those 3 things on our list, or address all 3 of those things on our list when we are searching for extrema for our function. Okay. On your derivative, so not on your function itself. So on your function, that might be at a corner, a cusp, discontinuity. Remember, like the things that make a derivative fail to exist? Yeah. All right. Anyone still need this page? Okay. So let's go into an actual example here where it's asking us to find extrema. So it says find the extreme values, find the maxes and mins, all of them, local and absolute, of f of x equals x to the 2/3 on the interval from -2 to 3. Now it does say use analytic methods and not a graphing calculator to do this, so we're not going to basically what they're not allowing us to do is graph a picture and use your calculator to find the maxes and mins. Okay, so we have to go through what we just talked about in order to find that. And so one of the things is, if I think about the extreme value theorem, I know that this function right here is going to have both a max and a min. And the reason I know that is this is a continuous function. There is no domain restriction, right? And it is on a closed interval. So the places that those maxes and mins are going to be located are on this list, as we're going to go through that list and we're going to look at the endpoints and then where our derivative is 0 and where our derivative is undefined and collect all of those possible locations and see if any of them are maxes or mins. If we look at this, it does give us an interval, so I'm going to eventually make a table of all of those different types of values. One of those would be my endpoint. So I have an endpoint of -2, and we're going to come back to this table in just a little bit. We have an endpoint of 3. And then we will also add to that list of possible locations of maxes and mins any critical points. So now let's talk about the critical points of this function. Remember that critical points will happen at one of 2 places, where our derivative equals 0 or where our derivative is undefined, which means we got to go find our derivative, right? So let's go find our derivative. Our function is f of x equals x to the 2/3. That's just a power rule. So our derivative would be 2/3 x to the 2/3 minus 1 would be -1/3. Okay, good so far. I will tell you right now that that was great until now we need to use it to do things like find where it equals 0 and find where it's undefined. And a lot of times that's going to be easier if we rewrite it. This format is a lot easier to take my derivative of, but the other format where we look at it as things like radicals and fractions is a lot easier to decide where things are 0. So I would rewrite this, changing this to the bottom of my fraction and back into a radical, right? So that 2 is going to stay in the top. This x to the 1/3 is going to go to being a cube root of x in the denominator of my fraction. So if we are talking rational functions, remember that rational functions, if we want a rational function to equal 0, that's when your numerator is going to equal 0. right? I can also just set the entire thing equal to 0 to remind myself of that. But it's really when your numerator is equal to 0. But when does 2 equal 0? Never. Okay, so is this function ever going to equal 0? No. So we don't get any critical points from this possibility. Then we talk about the other possibility. When is this function undefined? And again, when would a fraction be undefined? The fraction is going to be undefined when the denominator equals 0. Okay? So then I go to that fraction and I set my denominator equal to 0 to find points where it is undefined. If I use my algebra to solve this, 0 divided by 3 is 0. Cube both sides, and 0 cubed is 0. This function is going to be undefined when x equals 0. So then I can add that point. That is a critical point. I add that into my list over here. And my list is made up of all the endpoints and then critical points of my function, of my derivative. Okay? Good so far? All right, so then how do we find the actual values? Well, remember, this is we are looking for extrema of f. So we are looking for these points on f. So we are going to take these x values, so to get our y column, we plug those into our function, the original function. Now, it did say not to use a graphing calculator, so I would be plugging these in by hand, which is not super pretty, but let's go through that. Okay, so negative 2 raised to the 2/3 is negative 2 squared cube root, right? Cube root of negative 2 squared, right? Negative 2 squared is 4. We're looking at the cube root of 4. Which I know is going to be something less than 2 because the square root of 4 is 2, so the cube root is going to be something less than 2, right? Do that same thing with 0. Okay, well that's going to be 0. Do the same thing with 3. And that's going to end up being 9. Cube root of 9. Something a little bit bigger than 2, right? Because the cube root of 8 would be 2, so the cube root of 9's got to be slightly bigger than that. I don't know, 2 point something. And this would be less than 2, 1 point something, right? Okay, so looking at those, we can then classify. At each of those locations, we are looking at a extrema. What type of extrema are we looking at? So, as we look at this function, we've got 1, 0, and 1 point something, 0, and 2 point something. Well, what is our maximum? 2 point something, right? And that's the highest point in that whole thing. So that would be called an absolute max of our value, cube root of 9, at our x of 3. What about our minimum? What's the smallest number up there? 0, okay? So don't overthink the table. That's exactly how you identify these things. The biggest number is the max, the smallest number is the min. So the absolute min is 0, of 0, at 0. So then what's this? What are we looking at here? It's a relative maximum, right? It's a relative maximum at negative 2. Not the highest point, but it's higher than what's around it. Cube root of 4 at x equals negative 2. Okay. Right. So one of the things we can do, how do I know if it's a max or a min if it's just 1 point? Compared to the points that are around it, it would have gone from this point to this point, going from 0 up to 1 point something, which means this point is higher than the one that's next to it, making it a relative maximum. How do I know that it didn't hit a max and come back down to that point? We don't have another max on that list. Otherwise, we would have had another max on that list. Okay, so does that make sense? And we're going to look at one like that, where it hits a critical point but doesn't actually make it a max or a min. We'll look at that as well. Yeah. Yep. Questions. Now, do you guys remember, I don't know if you remember seeing something like this. We used an example like x to the 2/3 at the beginning of the year when we talked about when a derivative fails to exist. This was an example of one of the cusps. If you were to type this into your calculator, we would be looking at a function that looks something like this. Okay, and we were supposed to look at it from -2 to 3. So it'd be just this part of it. Can you see what we just figured out? That that's the absolute minimum, that's the absolute maximum, and that's a relative maximum. Okay, and we use that to help us identify each of those locations. So there's what you're looking at. If it asks us to confirm on a calculator, that's what we would see when we type that function into our calculator. Okay, questions? All right. On this next one, sometimes when they are asking you to find extrema, they will not specify a domain, but that does not mean that your domain is unrestricted. So sometimes you have to remember that functions themselves can bring to the table a domain restriction. On this one, it asks us to find the extreme values of f of x equals 1 over the square root of 4 minus x squared. Now, kind of fly through this part of it, but this does have a domain restriction, right? I cannot plug just any old x into this function because, like, if I were to plug 10 in here, I would have 4 minus 100, and I would be taking the square root of -96. I can't do that, can I? Because I can't have the square root of a negative. So radicals in the bottom of a fraction, bring with it domain restrictions. I can only put x's in here such that this is a non-zero positive number. This one's a little bit weird, but that means that I need to be subtracting something that is less than 4, right? Because if I subtract 4, this becomes 0. So the biggest x squared would be up to 4, but not including 4. Well, it's squared, so that would actually be x can get up to 2, right? You following all of this? So kind of flying through the domain of this one, x could be 2, but we are squaring it, so it actually could be down to -2. If we were to pick anything between those, no problem. If I pick something bigger than 2, problem, right? It's now square rooting a negative, which we can't do. Do I get to include those in my domain? No. If I include 2 in my domain, I now have the square root of 0, which is 0, and now I have a 0 in the bottom of my fraction. So those are not actually included. We're going to come back to that in just a second. Okay, so that, keeping in mind our domain restrictions on this. This function exists from -2 to 2, not including those. So then it says, find the extreme values of this function. Now we are not guaranteed a max or a min on this one because it does not have a closed interval, right? It didn't ask us to look at a closed interval. So we are not guaranteed maxes or mins. We don't have endpoints to put on our table. I can look at critical points. So let's look at the critical points of this function, which again will be at 2 places, where our derivative equals 0 and where our derivative is undefined, which means we need to go find our derivative. When dealing with a derivative of something like that, I think it's going to be easiest for us to rewrite that function. I would just slide that to the top, make it a fraction exponent, so this would be 4 minus x squared raised to the -1/2. Same function, right? I haven't changed anything yet, I just made it look different. Now taking the derivative of it, we're looking at a chain rule here. The derivative of the outside would be an x raised to the -1/2, which would make that -1/2, subtract 1, -3/2. Don't change the inside. Times the derivative of the inside, and the derivative of 4 is 0. The derivative of -x squared would be -2x. And again, I really think it's going to be easiest for you to figure out when your derivative is 0 and when your derivative is undefined if you go ahead and make all of your fraction exponents back into radicals, make all your negative exponents back into fractions, all of that. So cleaning this one up, first of all, -1/2 times -2 would be a +1, right? The x is going to stay in our numerator, but this parentheses is going to move back to our denominator because of the negative and become a fraction, a radical because of the fraction exponent. So this is a 4 minus x squared cubed inside of a square root. Writing it in that format is going to help us think through our zeros and undefines a little bit easier, I think. So again, if we are looking at a rational function, a fraction, our derivative will equal 0 when the numerator equals 0. So that I can set my numerator equal to 0 and solve. Our derivative is 0 when x equals 0. Questions? Okay. So when would it be undefined? Well, it's going to be undefined and irrational when our denominator equals 0. So I would set my denominator equal to 0 and solve. Okay, so square both sides, right, which would give me 4 minus x squared cubed, still equal to 0. Cube root both sides, which would give me 4 minus x squared, still equals 0. Get that x squared by itself, divide by -1. We're looking at x squared equals 4, square root both sides, x equals plus or minus 2. Okay, so I have critical points now. I've got 3 critical points, 0, 2, and -2. But guys, when I come over to my table, I am only going to put 0 on my table. Tell me why I am not including the other critical points on that one. What's that? Our function is undefined there, right? Our function is not defined at -2 and 2. That's not in the domain of our function. So if you find a critical point that is not in the domain of your function, it is not included as a critical point. It's not even on your function, right? This function doesn't exist there. So I won't put that there. We have 1 critical point. Great. We treat it just like we did last time. I plug that 0 in, and I get, let's see, 1 over 4 minus 0, or square root of 4 is 2. So we get 1/2, or 0.5. And I'm going to write it as 0.5 for just a second here, for a reason. Great. That's a max or a min. It's 0.5, but I don't know if it's a max or a min, do I? I know it's a max or a min, but I don't know what it is. So how do I figure out what it is? Guys, I just pick points around it, because the points around it are going to either be above it or below it, because it's either going up to 0.5 and coming back down, or it was up at something, comes down and hits 0.5 and goes back up, right? That's what's going to make it a max or a min. So then I just pick sample points around 0 to figure out what it is. So something like -1 and +1, if I were to look at the other sides of it, it'll tell me what it's doing on either side of 0. If I plug -1 into our function, I would have 1 over 4 minus 1, which is 3. 1 over the square root of 3 comes out to something ugly. 1 divided by the square root of 3, 0.577. Okay. I get the exact same thing when I plug 1 into that, right? It's still 1 over the square root of 4 minus 1, or 1 over the square root of 3.577. So these were higher. They came down and hit 0.5, went back up, which makes this a minimum. We are looking at a absolute minimum of 0.5 at x equals 0. Now remember, the others that I put on that list are not extrema. I just had to look at them to see what I was dealing with, a max or a min. Questions? All right. Next one. Find the extreme values, verify on our graphing calculators. Our function this time is f of x equals e to the negative x, and we are looking from -1 to 1. And they can write the interval like that, -1 is less than or equal to x is less than or equal to 1. Is that an open or a closed? closed, right? Because it says or equal to. So that is important to us. Because it is a closed interval, which we've been seeing written like this up till this point, same exact thing, right? Because it's a closed interval, I know at the end of this I should have at a minimum a max and a min. I could have some additional, like we could have more than that, but I know that I'll have at least one of each. Okay? First of all, I know that those numbers get put on my table. I include the endpoints. And then we're going to go check for critical points and see if there are any critical points in this one. So we will check when our derivative is equal to 0. We will check when our derivative is undefined. Let's find our derivative. We have to remember how to take the derivative of an exponential. So exponential derivative e to the negative x is going to be e to the negative x times the derivative of the exponent. And the derivative of negative x is negative 1, right? Now, I'm going to clean this up and put that negative out front, but I'm also going to drop this e to the x down to the bottom of my fraction. Again, I think it's easiest to make all of your exponents positive if you can, make them back into radicals if you can, when trying to think through the whole, when is this going to be 0, when is this going to be undefined thought process. Okay, well, if that's my fraction, negative 1 over e to the x, when is it going to equal 0? It's not, is it? There is nothing I can plug into this that is going to make this equal 0. Okay, so this will be never. And again, seeing it as a fraction, probably a little easier for me to think through that answer. Okay, when is this going to be undefined? Well, it would be undefined when our denominator equals 0. This is where we have to remember a little bit about exponential functions. When will e to the x equal 0? Never. There is not a number I can plug into there that would make e equal 0. Okay? It can be a really small fraction, but it'll never, I don't know if you remember the picture of an e to the x graph, right? It comes in flat lines right along there. Okay? It's never going to equal 0. So again, never here. So given this function, we have no critical points to add to that table. Our maxes and mins are going to happen at the endpoints. So now I just need to look at those endpoints, plug them into my function, see what they are, and that'll help me identify which one's the max and which one's the min, because there they are, my max and min. So the first one is plugging in negative 1, which would be e to the negative 1, or e to the first, which is e, and e to the, how many decimal points should I make this? That's not a trick question. Always. 3, right? I never have to tell you how many decimals. Guys, that doesn't change. Even on your tests, it doesn't change. We will talk later. Okay. 2.718, and then e to the negative 1, which is 0.36. Those of you looking at your calculators, that is 0.368, if I round correctly. So then I can completely identify that I have a absolute max of 2.718 at x equals negative 1, or e at x equals negative 1. I have an absolute min of 0.368, or 1 over e, at x equals 1. Done. Side note, 1 over e, the 0.36, it's actually on your calculator, 0.367,879, whatever. Guys, if you round that wrong, guess what the AP does? Checks it wrong. You did like the whole thing right and you rounded a number wrong and you get the whole thing wrong, okay? So please hear my voice in the back of your head right when you go to write down a decimal. Round correctly. Go back to When did you learn how to round? Elementary school? Elementary? Yeah? Yeah. Round correctly. For some reason, I was feeling really nice on your last test, but some of us work on your rounding. All right. We're going to skip that one and go to this one because of time. But kind of a question I think Kaya might have asked earlier. Think about the function itself can help us kind of frame what we should be expecting for answers. So if we were to think about this one, it says find the extreme values. It does not give us an interval to look at, right? So I'm not guaranteed anything. But if we think about the shape of the graph, guys, go back to your parent function. What is an x cubed look like? That, right? It might twist and turn in the middle, but it's going to look something like this, right? Okay, well, what does that tell you in the whole frame of extreme values? You know, it's an x cubed. What can I already tell you about the extreme values? I don't know anything else about this function, but I can tell you something. There are no absolutes, right? There are no absolute maxes and mins. Now, have you seen a cubic graph that does something like this? Does that have maxes and mins? But they will be local, won't they? They will not be absolute. So I know that that kind of helps me think through this one as to whether or not I would have absolute maxes or mins. I can't because of the function itself. Now, going through then, there's no interval for endpoints, but I can look at my critical points, which means I need to look at my derivative. Just power rule all the way across, right? So again, thinking through my critical points, I need to think of two places. Where does my derivative equal 0? Where is my derivative undefined? Are the two things I think through. That can equal 0, so if I set that equal to 0 and solve, factor and or quadratic formula, right? It's a quadratic, so that's my options. There is a GCF. It's going to make this one a little easier for you. Are there factors of 1 that add up to -2? Please say yes. Yes, right? -1 and -1. Okay. Anything that has an x gets set equal to 0. Why did I just say that? 3 does not give us a 0 on this, right? I know it's a GCF, and sometimes GCFs will add to our list, but this does not have an x. So our only answers come from there, which means that's actually the same thing. We have a critical point at 1. Where is that function undefined? Nowhere. It doesn't have a domain restriction, right? There's nothing that's going to make it undefined. So we have one critical point to look at, which again goes back to the idea of, I'm going to have to figure out some stuff going on around it to see what we're looking at here. So plugging 1 back into this function, I would get 1 minus 3 plus 3 minus 2, right? Should be -1. Which doesn't tell me max or min necessarily, which means I need to look at the function around it. If I look at some points around it, if I plug 0 in here, I get -2. If I plug 2 in here, I get, what, minus 12 plus 6 minus 2, 0. Okay, so what am I looking at here? I'm looking at a function that's continually increasing through that point. Right? So not a max or a min, are we? That is not a max or min, and I can see that with the values around it. We have no extrema on this graph. Any questions? I know we kind of got rushed here at the end, so we will pick up there. Your assignment is out of the book today.